Hello everyone. Thank you for joining us. In today's webinar, we will demonstrate how EMS for SolidWorks software can be utilized to study high-power bus bars. We will cover various topics including analyzing bus bars under AC and transient conditions, computation of inductance, resistance, eddy currents, losses, and multiphysics analysis like thermal and linear statics. Before discussing today's agenda, let me introduce us. My name is Cal and I handle sales and marketing division of our company. My colleague Majdi works as an application engineer and technical support expert. He is an experienced user of EMS and EMWorks2D software products and has extensive knowledge in low frequency electromagnetics. He will be delivering the technical part of today's webinar. Before moving on, I would like to highlight few points. During this course of presentation, if you have any questions, please feel free to use the chat window to type in your questions. We will answer them at the end of this presentation or will reply to you via emails. A webinar recording link will be sent to all the registrants in a few days. Moving on to the agenda of today's presentation, I will briefly talk about our company EMWorks and various products we offer. Then my colleague will present the technical part of this webinar. At the end of the technical presentation, I will talk about various learning resources offered by EMWorks for its software users. Now let us take a quick overview on our company EMWorks. We offer 3D and 2D electromagnetic simulation software as an add-in tool for SolidWorks and Autodesk Inventor 3D CAD. Our company was founded in the year 2000. We have a vast sales network in the form of 2 offices and a global reseller channel. We provide our solutions and services directly or through a reseller in America, Europe, and Asia Pacific region. Our company has a strong research and development team with years of experience in the field of electromagnetics. In addition, our products are gold certified by Dassault Systems SolidWorks Corporation since the year 2008. We have 2 office locations. Our headquarters is in Montreal, Canada, and we have another office in Germany. We offer 4 products with various add-ons covering a wide frequency range. Our first product is called EMS, which is used for electric and magnetic field modeling for low frequency applications. It covers many applications like insulators, cables, bus bars, permanent magnets, actuators, circuit breakers, transformers, and electrical machines. Our second product is called EMWorks, which is used for electromagnetic simulation of RF, microwave, high frequency and high speed electrical and electronic devices. It covers applications including wide range of antennas, resonators, filters, connectors, and waveguides. Our third product is called EMWorks2D, which currently offers static analysis and covers simulation of planar and axisymmetric geometries. Our latest addition is Motor Wizard software, which is a template-based motor design tool. It offers analytical and finite element analysis of brushless DC electrical machines. In addition to these solutions, we offer few multiphysics add-ons like thermal, motion, linear statics, and circuits. In today's webinar, we will demonstrate analysis of bus bars using EMS software. Now let us talk a little bit about our licensing structure. EMWorks offers 3 different programs: commercial, academic, and startup. Each of these programs has its own benefits and requirements. Within commercial program, we offer perpetual licenses, while in the rest of the 2 programs, our licensing structure is annual based. Now I would request my colleague Majdi to take over and present the next part of this webinar. Thank you.
Thank you, Carl. Hello, dear attendees. Thank you all for joining us today. I am Majdi, Senior Application Engineer at EMWorks, and I'm going to deliver the technical part of today's session, which is about how to design a high-power bus bar using EMS for and EMWorks2D for SolidWorks. In this webinar, we are gonna present to you our complete solution inside SolidWorks to design and study wide range of busbars applications from simple to complicated ones. Therefore, we start by an overview where we will see the main design issues posed by busbars applications and our proposed solutions that can solve these challenges and meet the needed requirements. Our presentation will cover static, transient, and harmonic magnetic analysis with both full 3D geometry and 2D approximated models. Shielding effect of ferromagnetic screens will be studied and short circuit response of the busbars will be analyzed to see its impact on the application function. Before concluding, we will go through temperature and structural analysis performed by EMS multiphysics capabilities. As you already know, busbars composed of a single or a group of conductors are used as an electrical junction between incoming and outgoing electrical currents. Some typical applications of these devices can be to form the interconnection of the incoming and outgoing electrical transmission lines and transformers to an electrical substations. They are made usually of copper or aluminum in tubular or rectangular or flat shapes depending on their application and the amount of currents will be transmitted. The issues that need to be addressed in the design of busbar systems include temperature rise due to energy losses, energy efficiency, and lifetime cost, short circuit currents, stresses and protections, and maintenance. Such application represents a multiphysics problem that includes electromagnetic fields, heat transfer, and structural stresses. This requires a complete platform where all these solvers can be grouped. This platform can help to overcome the design issues that arise during studying busbars. Let's have a look of these challenges and what we will propose as a solution. The challenges, as we have seen, busbars can have different bar shapes and configurations. Then a flexible and powerful CAD tool is needed like SolidWorks. It comes with several features that make geometrical modeling easy and fast. Inductance and resistances of the busbars are important parameters that need to be determined by simulations before going to lab measurement, since it may be complicated process. By its static, harmonic, and transient magnetic solvers, both EMS and EMWorks2D can help to predict accurately these different quantities and save effort and time to market. In addition to these parameters, losses including DC and AC losses are main factors that affect the efficiency and the service life of busbars. The bars materials and configurations can play an important role in increasing or decreasing the bars losses, and hence the temperature caused by these losses. Parameterization feature provided by EMS and EMWorks2D helps to parameterize different variables types like geometrical and simulation parameters. It is useful to compute losses for different geometry and materials. Also, electromagnetic losses with magnetic forces can generate structural deformation in the conductors and the metallic housing. These impacts became more important when short circuit occurs in the busbars. The coupling to thermal and structural solvers is performed within the same study and inside same environment. No import or export of data for efficient and accurate results. During our presentation, we are going to see these features and understand their importance in any busbars design process. While designing busbars, we may start by a simple model that represents an axial symmetry. Hence, a 2D solution can be used to solve such problem. EMWorks2D, which is our electromagnetic 2D software, is fully integrated inside SolidWorks. Let's have a look, or let's have a quick look at it before continuing with our presentation. Both EMS and EMWorks2D are integrated inside SolidWorks, where 2D model can be made through two ways, whether by converting an existing 3D geometry like this or into simplified geometry, or create a 2D model from scratch using SolidWorks sketches and surfaces. The conversion from 3D to 2D is automated by EMWorks. You need to define your symmetry coordinate system like this one. This coordinate system, this local coordinate system, and apply 2D simplification feature of EMWorks2D. Let's go to EMWorks2D tab, click here, 2D simplification, choose our defined local coordinate system, and we choose the symmetry type, whether it is planar or axisymmetric. Then apply the 2D simplification. After a few clicks, you will get your 2D geometry, but with keeping your 3D as well. So if you have EMS and EMWorks, you can use both of them at the same time and with the same model. So as you can see, we still have our 3D model. We can use this feature, show 2D model. So now you see our 2D model standalone. So we can show both of them at the same time. So there is a surface here. Let me show you. So we have surface bodies and volume bodies. So we still have the 3D geometry, and we created another 2D geometry, so we can do simulation with EMS and EMWorks2D. Let's go back now to our presentation. As you can see at the bottom of the slide, two figures showing the magnetic field results with superimposing the field lines. In this case, no shielding is applied, so the flux go from one line or one phase to another phase freely, which will increase the proximity effect in case of using AC currents. As you can see at the right or at the bottom right figure, we are plotting the field lines while we can see the 3D geometry. Continuing with the static analysis, and since all the three phases are identical and have same spacing, DC resistances and inductances are the same. DC losses obtained by the software is proportional to the applied current, which meets the theory. It can reach values of 5 kilowatts when 10 kiloamps are applied. At the top right side, we can see the magnetic field results between 2 points at the axis of the busbars for different currents. This figure, so you can see the magnetic field between this point and this point. So there is a distance of around 2.4 meters between these 2 points. So, and we have several curves for several currents. So we can see, for example, the top curve that the current is 10 kiloamp. The magnetic flux can reach 0.1 Tesla at the first or at the extremity of these busbars. So this plot shows that the flux is a bit smaller at the middle phase compared to line 1 and line 3. We can see the impact of these results at the bottom right image that shows the Lorentz force results. This figure shows the Lorentz force results for the 3 phases. So we can see this one, it is the line 1, the middle one, this represented by the green curve, and the red curve represented line 3 results. Force, I mean. So line 1 and line 3 have higher force results compared to the middle line, which is almost 0. This is because of the effect of low field around the middle phase bars. So now let's move to another complicated 3D geometry that needs a 3D software. Usually bus bars are a combination of multiple bars with different shapes and connections. They may contain hundreds of bars. Hence, our 3D electromagnetic software EMS can be used for such application. EMS is fully embedded inside SolidWorks, like EMWorks2D, as we have seen. So we can discover EMS for SolidWorks. So let's have a quick look. So as we said, EMS is also like EMWorks2D is fully embedded inside SolidWorks. So both of them, EMS as well as EMWorks2D, they have the same look and feel as SolidWorks. So EMS comes with 6 modules. Let me create study. So as you can see, EMS comes with 6 modules, 6 electric and magnetic modules, from static to harmonic and transient regime. So it covers, so EMS helps to cover a wide range of applications like motors, generators, high power insulators, eddy currents problems, and so on. It allows also to couple electromagnetic studies with few multiphysics options like thermal coupling, let me see here, so like thermal coupling, linear static coupling, the coupling to SolidWorks motion, and the possibility to couple your electromagnetic analysis with external circuit. So this is possible in AC magnetic and transient magnetic. So as you can see, we can couple our study with circuit. Let's see. So EMS contains a rich and well-organized material library that contains wide range of materials and material types. So you can see from cables, ceramics, conductors, electrical steel with BH curves, PB curves, and all the needed properties. So permanent magnets, a wide range of permanent magnets library, and so on. Also, a user can add or customize his material using this library. So it's possible to define or import your material from outside this library. Back now to our presentation. A 3D model of bus bars is solved with EMS. This complicated 3D model is solved with EMS to compute DC loss after applying 5 kiloamps to each phase. DC conduction or magnetostatic modules, both of them can be used to get these results. DC conduction doesn't require an outer region, hence it may be used for simplicity of the problem. The shown results represent the current distribution of the simulated bus bars. We can plot fringe and vector plots, and also we have the option of streamlines plots. And in this slide we can see the bus bars DC resistance of each phase. They have different results since they don't have the same geometry. The DC losses of this model can reach values of 16 kilowatts if the applied current is 10 kiloamps. Now EMWorks2D is used again to solve the 2D model of the bus bars under alternating current. So now we have a varying current, time varying current. For this purpose, the the transient module if EMWorks2D is used. Magnetic field results versus time are shown in this slide. So we can see the animation of the field lines when the currents change their shift angle. As can be seen from the top left figure, the current density has a non-uniform distribution along the conductor's thickness, and this can be confirmed by this plot, So you can see the current density inside one conductor, it increases with the conductor depth, so it is not uniform, it varies. This behavior is due to the proximity effects caused by the other busbars phases. The impact of skin effect is neglected here since the frequency is low and the skin depth is big enough compared to the conductor's geometry. The total ohmic losses are represented by this figure. It oscillates between 500 watt and 1500 watts, and the loss forces are represented by this right bottom figure. The average force of the middle line is around 0 like in the static simulation. Now we have a model that doesn't represent any symmetry and cannot be solved with a 2D approximated solution. Hence, EMS again is needed to handle this type of problem. This model contains two bars per phase and supplied with a rated current of 5 kiloamps at the frequency of 50 Hz. In this simulation, the transient module of EMS is used to compute the electromagnetic results versus time and before reaching the steady state. The magnetic flux density results are shown in this slide. An animation versus time of the field plot is used to illustrate the transient results. The red zones and the bars are due to the proximity effects. The current density distribution are plotted in these figures. An accumulation of the current at the adjacent edges of the phases can be noted because of edge and proximity effects. We can see an animation of the current distribution represented by vector. This video animation is saved and exported from EMS. So we can see here the accumulation of the current results in the edges. So it is due to the edge and proximity effects. The total AC losses versus time are given by the left figure. The losses are around 700 watt, while the figure at the right side shows X, Y, and Z components of Lorentz force of the first busbar phase versus time. Using the same model, we perform the steady state analysis with AC magnetic module of EMS. The proximity effect is now clearer from these figures. An isoplot can be used to identify regions with some specific values like what is shown in the bottom right graph. So as we can see here in this figure, we can see the red zones that represent the proximity effects. Here also in the current density results, we can see these red zones at the edges of the bars, and this plot, which is created by an ISO feature, which is post-processing feature of EMS, it helps to generate plots with specific values. So we only see regions with the specified magnetic or current density values that we defined. As we mentioned at the beginning, AC resistances and inductances are important parameters for busbars designing process. So our AC magnetic module helps busbar designer to get these results easily. If they don't need these results, we have an option to skip these parameters calculation, and this will save more computation time. It will directly compute only the losses. AC losses for two different materials, copper and aluminium, which are the most usual used materials for bus bars, are computed and compared to DC losses. We can see that aluminium generates more losses than copper, and this is normal since it has higher electrical resistivity. The ratio of AC over DC losses is around 1.4 for the copper and 1.25 for the aluminium. In both cases, the ratio is low because the frequency is low and we have a limited number of bars. To understand the impact of the frequency on the AC losses, we ran a frequency parameterized study using EMS. We can see from the current density animation versus frequency that the proximity and the skin effects became more important when increasing the current frequency. So as you can see here that these region at the edges became smaller, so the accumulation of the current becomes in limited or a reduced area at the edges and at the skin depth. The middle graph confirms these results. It can be seen that the AC resistance of the three phases increases with the frequency due to the skin and proximity effects. In turn, this augmentation leads to increase the AC losses since losses and resistance are proportional. As we said earlier, many factors can have great impacts on the busbar efficiency and losses. In addition to frequency, we can see in this slide the impact of the supplied current and the phase enter spacing. Concerning the supplied current and like the resistance, the losses are proportional to the current. As you can see here, the current density increases versus the applied current, and this is normal, and also the AC losses increases versus current. So we reached values of losses around close to 10 kilowatts when the current is around 18 kiloamps. And these losses are inversely proportional to the spacing. The distance between the phases is parameterized and the results are computed for different distance values. So from the animation we can see the red zones are being reduced. So these red zones are being reduced by increasing this spacing, which means that there is no big proximity impact and the resistance of the phases will decrease. Hence, the AC losses in turn will be reduced. This may give us an idea how to arrange the bars in a limited area while keep the losses as minimum as possible. As you can see here, the AC losses decreased from a value of 1440 watts to values around 1320 watts. Shielding in bus bars are very crucial. It helps to reduce some electromagnetic effects and limit the losses and protect electronic components from electromagnetic interferences. In this example, the 2D solution is used to compare two models with ferromagnetic screens. We can see that with screens, the magnetic fields are limited within the same phase and have less impacts in other components. Doing experimental short circuit testing is no more practical since it may cause the damage of electrical components. So the best place where you can analyze a real short circuit is by using simulation software. This helps to avoid any damage and save time. In this case, we assume that we have a short circuit current with a peak of 30 kiloamps for a period of 80 milliseconds. Using transient module of EMS, both the losses and the Lorentz force for each phase are computed. They represent important values. They may overheat the bus bars and lead to the deformation of the structure. This test is also needed to design the protection components. EMS coupled to both thermal and structural solvers helps to predict the heat generated by electromagnetic losses and the mechanical stresses caused by the combination of magnetic forces and thermal stresses caused by short circuit condition. The left figure shows the heat generated in the bus bars, while the other figures give an idea about the deformation of the bars. Here another full bus bar example where the temperature is computed versus two different materials. We can see that the temperature is bigger or higher when using aluminum as material, and it is expected since it has higher electrical resistivity. We can see also some temperature at the metallic part that plays a role of shielding of the circuit breaker. To summarize, EMS and EMWorks2D, both inside SolidWorks, covered different design challenges posed by the bus bars applications. DC and AC losses were computed. The bus bars different parameters including inductance and resistance were calculated. Skin and proximity effects were evaluated. Shield effect was studied, and finally the temperature and mechanical stresses were estimated. Thank you for your attention, and I hand over the screen again to my colleague Carl to continue the presentation.
Thank you, Majdi. In the technical presentation, we saw EMS product being used to study bus bars. Let us take a quick overview on this product. EMS software offers electrical and magnetic solvers. In addition, few multiphysics options are available like thermal, motion, linear statics, and circuits. This product is available in 4 package options: electric, magnetic, professional, and premium. To get more information on the software packaging and pricing, you can connect with me after this webinar. To perform electromagnetic and multiphysics analysis of high-power bus bars, EMS Professional package with thermal and linear statics add-ons should be used. Electric solver can be used to compute electrical fields and current density distribution, while magnetic solvers can be used to compute magnetic fields and losses. Thermal analysis can help a user to study temperature distribution, while linear statics can compute stress and strain results. Now let us do a quick recap on EMWorks products and their related applications. We can divide EMWorks offerings into 2 categories: applications related to low frequency simulation and applications related to high frequency simulation. Within low frequency category, we offer 3 products: EMS3D, EMWorks2D, and Motor Wizard. These products can be used to design and simulate applications like cables, insulators, bus bars, solenoids, magnet arrays, eddy current braking systems, wireless charging devices, transformers, and electrical machines. Within high frequency category, we offer one product, EMWorks. This product can be used to design and simulate high frequency applications like antennas, waveguides, filters, resonators, and connectors. Coming to the learning resources, we offer various free learning tools. With the software purchase or an evaluation license, users can access the demo viewer section of the software, through which they can access many predefined model examples and tutorials. In addition, we post application notes, blogs, and videos on our website and social media channels regularly. We also offer paid customized training sessions to all the users of EMWorks software. Anyone interested to get more information on our products, including a trial license, quotation, can go to our Contact Us page on EMWorks website, select the appropriate category, fill in your information, and submit your request. One of our representatives will reach out to you soon. I would like to thank you all on behalf of EMWorks for participating in this webinar. feel free to contact us after this webinar to get more information on our products. Thank you.